Thanks everyone for joining us this morning. And we have two interesting speakers today. The first speaker is Alejandro Torres, and he'll be telling us about exciting modes of gravitational waves due to the motion of the sources, and I guess the sources being memories. Please take it away, Alejandro.
Okay, thank you. Welcome everyone. And first of all, I want to thank the organizers of the GrEAT webinar that they are giving me the chance to give this talk. As I said, I'm talking today about the exciting modes of gravitational waves due to a motion of the source, measurability for extreme mass ratios spirals. This presentation is based on these two papers, which I have published with my supervisors, Paola Sevane and Chen Chen here from the Pekin University, and also other collaborators, like for example, Alvin Chua. The content of our presentation is the following. First, I will talk about the motion of the source. So basically, why do we think or know that gravitational wave sources, in particular MRIs, are moving? This is related to the peculiar velocity of the galaxies. And then in the second part, I will talk about the effect of the motion on the gravitational radiation. So basically, what happens to the radiation patterns and how this is related to the modes of the gravitational waves. In the third part, I then will talk about the possibility to detecting the motion of MRIs using this effect and how accurate this can be done. So let's first start with the motion of the sources. The first thing to consider is that extreme mass ratio spirals are located inside galaxies. So usually they are this supermassive black hole in the center of the galaxy, which is being circled by some solar mass black hole, which just come from somewhere in the galaxy. So now, because these sources lie in the center of the galaxy, they of course move with the galaxy. Now, what happens? The point is that most of the galaxies, around 60% of them, are inside big clusters containing dozens to sometimes even hundreds of galaxies. And because we have this high number of galaxies, they of course build a very deep potential. And this deep potential causes your sources to be moving around. This, for example, has been measured for light. Here I have a plot of some measurements that have been performed for the velocity dispersion in several galaxy clusters, where each of these points represent a galaxy cluster. So each of these points represent dozens or hundreds of galaxies in there, where each of them could potentially be the host of some extreme mass ratio spiral. And as we can see, the average velocity dispersion for most of the galaxy clusters is something around 1,000 kilometers per second, with maybe a slight trend to having higher velocities the further you go out to higher redshifts. Now, the point is, because all of these galaxies are moving with this velocity of around 1,000 kilometers per second, and they cannot all of them be perfectly fine-tuned to the Earth, this basically means that they're also moving relative to the Earth or to detectors on Earth or following the Earth, like for example, a LISA-like detector, also with velocities of around 1,000 kilometers per second. On top of that, our galaxy, the Milky Way, is also inside the galaxy cluster. And this being inside the galaxy cluster also causes a motion. This also has been measured, which is, for example, shown in this plot, where the black line represents the average velocity of our galaxy relative to the background. By the background, we mean basically all other galaxies. So when you take the velocity, the relative velocity between our Earth and all other galaxies we can see in different galaxy clusters, you can find a dipole moment. This dipole moment suggests that our galaxy is moving with a velocity of around 400 kilometers per second, independent of the redshift, more or less, at least for low redshifts. Now, as I told you, this is being measured by taking the average velocity for all these distances. So of course, this means that there can be also some galaxies which are moving with higher velocities, 400 kilometers per second, again, something around 1,000 or even more kilometers per second. So in total, we can say that the hosts of the extreme mass ratio spirals are always moving with velocities, or almost always with velocities of around 1,000 kilometers per second relative to us. So therefore, we must consider that the extreme mass ratio spirals are moving also with a velocity of around 1,000 kilometers per second relative to us or to the detectors. So now let's talk why this is important for the gravitational radiation, which effects can appear when extreme mass ratio spirals or gravitational wave sources in general are moving with such velocities. Let's first talk briefly about the common current picture, which are the plane waves. For plane waves, by plane waves, we mean that only one dominant mode is being considered, usually the 2-2 mode. There, showed in 1986 that there is the so-called mass redshift degeneracy. This means basically that when a source is being redshifted, in the paper he discusses it was due to the expansion of the universe, but this can also be due to motion or other effects which can cause a redshift or a blue shift. The source will look exactly like the same source without redshift, but being more massive, or without blue shift being less massive. So this means in the plane wave limit, a moving source looks exactly the same as a non-moving source, which is just more massive or less massive. But gravitational waves are actually not plane waves, strictly speaking. This is because there is superposition of different modes, and these modes are related to the spherical properties of the source. Now, what happens when the source is moving? For that, let's look on this plot, where on the top, I show a gravitational wave source which is being at rest. Here on the left side, we have the plus polarization, and on the right side, the cross polarization. And in the lower part, we have a gravitational wave source which is moving. And now what happens is that when the source is moving due to different special relativistic effects, where the most important one is aberration, the radiation is being focused. Something similar exists for light, where you have the headlight effect, where you have a stronger emission of light in the direction of the motion. And this means that our pattern, which here on the top is quite regular because this is exactly the same source, just one at rest and now moving, has a slightly different radiation. Why is this important for the modes? This is because the modes of the gravitational wave source represent the spherical properties of the source. This is basically, to compute them, we have to take a combination of the plus polarization and the cross polarization and decompose it using the so-called spin-to-spherical harmonics. Spin-to-spherical harmonics are a basis of, let's say, shapes which you can use to decompose the shape you are trying to express. And now what happens when we have a quite regular source, almost isotropic? We see, for example, that the 2-2 mode, which is represented by a sphere, it's good enough to represent the sources. However, when we have now the same source, for example, moving, and we have that there is a stronger emission in a direction route, for example, let's say that it appears elongated in some direction, you might need other of these shapes to describe it. So physically, this means when the source is moving or is being distorted, it will contain additional modes, in particular additional higher modes. In one of the papers, what I did was really to compute, okay, what happens if we have a source which is moving? If we know the modes of the source in its own rest frame, and we consider now the source moving. And there I computed that for the modes of the moving source here on the left, they can be represented as the combination of the original modes plus some correction, which is proportional to the velocity, and again, a combination of the original modes times coefficient, which are different for the different modes. Now, what does this mean for the detections? The point is that the gravitational waves that we are getting are a combination of these different modes, where each mode usually is related to a particular frequency. And now all of these singular frequencies, which are being treated or are combined to a new wave, they have different contributions, and this will make that the gravitational waveform or the signal we get looks different. For that, let's look here on this left plot. In this left plot, I show a source which is moving in blue compared to the source in red. It's actually the same source, so with the difference that we have corrected for the redshift degeneracy. So if this would be only the 2-2 mode, this would be looking like the same waveform, so that there would be no difference. And also, it's important to highlight that we're considering the same ray. So, of course, because of the special relativistic transformations, in a coordinate system, they will look like different rays, but physically, we are looking exactly at the same ray to make sure that it's really the same source. And here we see that the waveform that we're getting, or the signal that we're getting, is indeed different. For example, in this case, the plus polarization is going to be a bit stronger for the moving source than for the one at rest, and the cross polarization is going to be significantly weaker. On top of that, and maybe more important, is there is also a difference in their phase. Their phase have a phase shift, which is on top of the time dependent. It is time dependent because the modes themselves are time dependent. So even though the velocity is constant, this different combination or different contributions from the different modes will lead to having a time dependent phase shift. Now, when we have a phase shift, or when we have a difference of waveforms in general, there is a good chance that we detect it. So the last thing we did was to consider, okay, is there a way to detect the motion for the extreme maceration spirals? So we took the waveforms for two extreme maceration spirals, where we assume that one is completely at rest and the one is moving with the aforementioned 1000 kilometers per second. So considering like this is a source inside some galaxy which is moving due to the peculiar velocity. Except of that, we did everything again like in the previous case. We corrected for the mass redshift degeneracy. We consider the same rate, so that we'll be considering like seeing the same, like the same source except of the difference of the velocity, basically. And what we did was first to compute the mismatch between the two waveforms, between the moving source and the non-moving one, assuming that we're observing this source for 2 years with the LISA-like detectors for the last 2 years before plunge. And here we can see for the mismatch, which is in blue, that when we get close to edge on, so to 90 degree means we're seeing the source from edge on, 0 degree means we're seeing it face on, 180 degree anti-face on, that there is going to be a significant mismatch between the two waveforms. That it is close to edge on is easy to understand because actually gravitational wave sources in general have more higher modes when they are seen from edge on, and having more higher modes makes this effect even stronger. And this is also important because for this case, we considered circular extreme maceration spiral for simplicity, and also because it's like a lower case limit. Most likely, most enemies will be highly eccentric, so they will have even higher modes, which will make these effects probably more important and easier to detect. Now, so that we, after knowing that, okay, there is going to be a mismatch and this could be quite significant, we also decided to look in which signal to noise ratio would be required to detect this difference in the mismatch. And here we see that when we are close to edge on, signal to noise ratio of something between 20 and 30 would be enough to see the difference in this waveform. 20 and 30 is nothing spectacular for extreme maceration spirals. It's more or less the minimum signal to noise ratio we're going to expect for most of the extreme maceration spirals that we are going to be able to detect. On top of that, if we relax our demand on the signal to noise ratio and say, okay, let's say a signal to noise ratio of around 100 is still very realistic for many extreme maceration spirals, we see that we will be able to see the difference between the moving and the non-moving source for inclinations of about 70 to 130 degrees. So for around 1/3 of the possible inclinations, and therefore we could say for maybe around 1/3 of the sources, we will be able to detect if the source is moving. The next question then to ask is, okay, how accurate are we going to be able to detect this? So for that, I performed a Fisher matrix analysis where we looked into the possibility of detecting the velocity, like how accurately we can detect the velocity, and plotted for that the confidence ellipses, and also the effect on the two masses of the source. Let's first look at the velocity, and there we see that for a source which is moving with 1000 kilometers per second, we should be able to detect this velocity with an accuracy of around 40 kilometers per second, which is at the 4% level. Of course, Fisher matrix is somehow idealistic, so in reality, it's probably going to be worse than this value, but even if it's 2, 3, 4 times worse than this value, we still would be at something at the maybe 10 to 20% level, which I think is quite good, considering that these are going to be sources at high redshifts, which we are going to detect. Now, when we look on the mass of the source, let's first tell you that we were considering a source where the primary mass was 10 to the 6, and where the secondary mass was 10 solar masses. So we see that we are going to detect these sources with an accuracy of around 10 to the minus 6, 10 to the minus 7, independent of if they are moving or not. However, one important point here to consider is that these two masses, or these 4 masses actually, of the sources are always in the rest frame of the observer. So, but we know that these sources are actually being redshifted. So considering that it's a velocity of around 1000 kilometers per second, the redshift will have an effect of around 10 to the minus 4. So 2 orders stronger than this. So why is this important? This is because these plots or these results are suggesting that we are going to detect the masses with an extremely high accuracy, if they are moving or not. But if the source is indeed moving and we are ignoring the velocity, we are overestimating how good our results are, or we are getting biased results for the mass. So actually, we really need to look for the velocity, not only for the purpose of understanding the velocity and seeing if the sources are moving, but really to be able to extract the information from these sources correctly. So that's also, to cut a long story short, let me please tell you a short summary of what I've been talking today. First of all, and probably most important, is that we have to consider that most of the host galaxies of extreme acceleration spirals are moving with velocities of around 1,000 kilometers per second relative to us. So we have to consider that the sources are really moving with quite high velocities relative to us. This velocity of the center of mass, or the center of mass motion of the sources, is going to excite additional gravitational modes, which will be helpful to break the mass redshift degeneracy. Using this difference and breaking the mass redshift degeneracy, we'll be able to detect the velocity of the gravitational wave sources and also of their hosts. So we will need this to detect the real parameters of the source, and it will also enable us with additional information about the sources and their hosts. So thank you very much. That's all. If you like the presentation, I would like to point you to these two papers, which are the two papers on which my presentation is based. Thanks again.
Thank you very much, Alejandro. Questions, please. Maybe I can start with one. It's interesting that this, excuse me, that you state that you can use this to break the mass redshift degeneracy. So would that have any impact on sort of detecting cosmology, doing cosmology and so on and so forth, without counterparts and the ladder?
For cosmology, let's say I haven't really looked into cosmology, what will be the effects there, but I think this is only going to work for the mass redshift degeneracy of motion. This is because basically this can be detected because the motion will cause, like, induce additional asymmetries, and these additional asymmetries or anisotropies are going to have an effect on the radiation. However, cosmology, which is based on the expansion of space-time, is not causing this kind of asymmetries, or at least I don't see how it can cause this kind of asymmetries, because the source is still the same source, and there is no like transformation, let's say like Lorentz transformation, which is causing a different shape or a different perception of this. So I think for cosmology, this is not going to help to break the mass redshift degeneracy, at least not in the same way. However, maybe there are also ways of changing the modes, or that no ways of changing mode. Maybe the modes will be changed somehow, which would also be helpful in that case, but this is something I haven't explored yet.
Okay, thanks. Yeah, I see what you mean. This is an effect of the dispersion of the peculiar velocity and not of the cosmological redshift. Is that what you're saying?
Yes.
Okay.
Yes.
Other questions? If not, then I have another question. So, regarding the issue about the peculiar velocity itself, I was just wondering, given that MRI is detectable by LISA or other space antennas, do we expect them to be very far out? I was under the impression that many of them would be relatively close, and if it's relatively close, it's possible to determine the peculiar velocity with complementary observations of those clusters, for example. Does that make sense?
Let's say how many MRIs and how far we are going to detect this is something which we only will be able to say for sure once we detect them. But depending on who you ask, or let's say more the common sense is that actually extreme acceleration spirals, of course, will be able to be detected being very close, but that in general, we are going to be able to detect them to redshifts which are higher than, for example, 1, which I'm showing here. Maybe up to 2. Some people say maybe we're going to be detect them up to redshifts of redshift 4. And with light, this is really more or less the limit. Around 1 is more or less the limit we are going to take. So I think with extreme mass radiation spiral, we can achieve more than with light, because in principle, we can see them further away. If we will be really able to assign then these velocities to particular clusters, having this high redshifts is another question, because like the accuracy of the sky location is maybe not good enough that we really can assign a particular MRI to a particular cluster. But at least, for example, at the statistical level, where we can see if there is really a trend of higher peculiar velocities going further out to higher redshift or something, that should be possible with MRIs, and I think we could do better, or maybe even much better than we can do up to now with lights.
Thank you. Yeah, that's a good point. Last chance for questions for Alejandro.
I have a quick question. That's okay.
Please go ahead, Ronaldas.
Thank you. I'm a bit surprised about this really huge effect on phase. So could you comment maybe a bit more about either like equations or why is it making so strong? Because like I would imagine that, well, you would expect gravitational waves from really like close to merging, and at close to merging you have like basically sources moving close to light. And you here have like dispersion velocity about 1,000 kilometers, which is not really that much in my opinion, like I would think. So there's really huge that really huge effect on phase. So could you comment on that? Maybe about theory or about equations, I do not know how, but like I'm a bit surprised about that huge effect on phase.
Okay, let's maybe go to this slide. First of all, this slide is for a LIGO source. So it's really a merger. And actually here in this plot, we're considering velocities, if I remember well, of 10,000 kilometers per second, just to make it possible to see it by eye. Actually, the effect, basically what happens is you have your modes, and your modes are becoming stronger in their amplitude by something proportional to the velocity. So for 1,000 meters per second, this is around at the 0.3% level. So what you're getting is just that some modes contribute a bit more. Now, because the different modes usually have different frequencies, so for example, if you only would have 2-2 mode, you would have a frequency of 2 times your orbital frequency. Now, if you get a little bit of the 3-3 mode, then the frequency of your wave is a superposition of something with 2 times your orbital frequency and something with 3 times your orbital frequency. So this will induce a phase shift. However, the case why we then studied this for extreme mass radiation spirals is because the phase shift is actually so small that you would never see it by eye in this kind of sources. So really, for this, we consider integration over 2 years of observation at for a signal-to-noise ratio of 100, which is, as I mentioned before, high, not extremely high, but still quite high. So, and you would need really like long observations and enough time to be able to see the phase shift. If we would consider this, for example, for a LIGO source, I mean, I tried doing this for LIGO sources, like with realistic cases we have up to now, and there we would need more velocities like of 3,000-4,000 kilometers per second to be able to resolve this. So something which is more similar to this than to the realistic cases of peculiar velocities. I don't know if this answers your question.
Yeah, that perfectly answers my question. Thank you.
Okay.
Sorry, just to clarify, when you say a LIGO source, do you mean something like a binary neutron star or a binary black hole or something like that? And
yes, for example, here this is just a binary black hole.
okay.
Where I assume it to be an asymmetric binary black hole, so that we have anyway higher modes from the start. For example, for LIGO up to now, we only have detected higher modes for asymmetric binaries.
Yes.
So we would need something like that to be able to get a region which is realistic to be detected. So
for sorry, go ahead.
For MRIs, we're anyway expecting higher modes. So it's going to be very likely that it's there. And here, as I also mentioned, this is for a circular binary. Actually, we expect MRIs to be non-circular, to have certain eccentricities, so that the modes will be a bit stronger, which would make maybe the detection of this a bit easier. But that's something I have to look into more detail, how the eccentricity really kicks in and how these shapes are at the end really changed. I guess that we will maybe be able to see more inclinations and just need a little bit lower signal to noise ratios.
Okay, very interesting. Any more questions for Alejandro? Okay, then let's all thank Alejandro again. Thank you very much for the very interesting talk. We should
Thank you
move
very
on.
much for your attention.
Thank you. And we should move on to our next speaker, Ronaldas Macas. Ronaldas? Oh, wait. Alejandro, can you stop sharing screen? Thank you.
Yes.
Okay, let me share my screen. Are you able to see my slides?
It's coming. Yes.
Okay, perfect. Hello, everyone. So today I will be talking about sky localization bias with non-Gaussian data. So firstly, why we should care about this? Well, contrary to what most people write, and they write that gravitational wave data is Gaussian and stationary, actually the gravitational wave data is non-Gaussian and non-stationary. And we say that it contains Morse artifacts, which we call glitches. And for example, in the first observing run of LIGO, in the first 50 days of observing, there was about 1 million glitches. And here on the right-hand side, you can see some examples of these glitches. And if I remember correctly, there was 3 signals, gravitational wave signals. So you can get the sense that there are way more glitches than signals. So because there are way more glitches than signals, we expect that there should be some glitches overlapping a gravitational wave signal. And we expect that they also affect parameter estimation of these gravitational wave signals. And this is especially important in low latency, because in low latency, we use parameters of that source to get the sky map. And then when we have the sky map in low latency, we send it to astronomers. So if the sky map, for example, is incorrect, then of course, like it's quite bad for astronomers. So one of the best examples for that is GW170817. So this is the first BNS signal that we detected. And during the detection, there was really huge glitch at Livingston data. So on the right-hand side, this is the plot of time frequency plot of the signal. So you can see the chirping signal of the BNS. And there's a huge glitch in the middle of that signal. And at that time, like 4 years ago, it was not really clear when we sent the sky map to astronomers if the sky map is affected by that glitch or not. And even more, when we get detectors more sensitive, we expect to have more signals. And because more signals, it means that it's more likely to have such cases to occur. So it's more likely to have a glitch overlapping a signal. And we already can see that in GWTC2. So this is the catalog for observing run 3A. And there was already 8 events that had such problems. There was an event, there were multiple events with glitches overlapping signals. And this is not really a problem for offline analysis for like parameter estimation, but it is really a problem in low latency because we do not have a method in low latency to remove glitches. So this is what we wanted to do. We wanted to see how much sky localization is affected in low latency. And for that, we basically simulated what would happen in real life scenario in low latency searches. So we just did some injections at specific times around glitch times. And for that, to detect signals, we use PyCBC Live. And when PyCBC Live detects signals, it sends the coincidence file to Baystar, and Baystar is used for estimating the sky map. And here you can see how it looks like essentially. We have BBH signal, then there's a blip glitch, and you basically get the sky map in the end. And because it is an injection, you know the true sky location. So you can compare those 2 things. And we, of course, do that for like multiple of times and multiple glitches also. So we see how the sky map changes over time relative to the glitch. So this is what we do. And as I mentioned previously, we are using PyCBC Live and Baystar like as in real life scenario. So we're using the same run parameters and we're using real O3 data. And furthermore, we are using 3 detector network. And the reason for that is that because for two detector cases, for two detector detections, there's really the sky error is quite huge. So we do not really expect to have much difference whether there is a glitch or there's no glitch. But when there's like three detectors, the sky location can get really good. And because of that, there can be some inaccuracies if there's a glitch, or at least we would expect to see some inaccuracies. And also we're using Livingston at the optimal orientation. So we make an injection such that it would be at the optimal orientation for Livingston. And this is just because we do not really want to look at the detector antenna pattern. We want to look at how the glitch affects the results. And we use quite high SNR. We use SNR 30 for Livingston. And this is again just to make sure that this is like a strong three detector detection. Because with two detectors, as I said, like you do not really care that much about glitches because the sky error is quite huge anyways. And with weak three detector detection, we also saw that there's really no much difference between Gaussian loss and glitches. So we looked at really like the stronger cases. So this is the network SNR 40. And then we looked at different type of signals. We looked at BBH signals, so like GW15 and N14, we looked at the BNS signals, and then we looked at NSBH type signals. So we use three types of signals, and then we use different types of glitches. We looked at blips, thunderstorms, and fast scatterings. And what we did, we basically took 10 blips, 10 thunderstorms, and 10 scatterings, and then we just ran these three types of signals for like these tons of signal, or these tons of glitches. Now there's one problem with that. The preliminary results have about 9,000 sky maps. So it would be a bit crazy to go through like all of these 9,000 sky maps. So we need to have like an effective quantity to measure sky maps. So we have a couple of those quantities. So one is credible area, which is just what is the area containing 50 or 90% probability. Then we also looked at maximum probability within certain square degrees. So these areas represent different telescopes. So there's like really small field of view telescopes, like half a square degree, and for example, really big EM telescopes, which are like 40 square degrees. So that's why we chose these values. Then we did something different, which is localization distance. We looked basically what is the distance between true sky location and the other location. So that other location can be maximum probability pixel location. And in this sky map, this would be this green star. And then true sky location versus the location of weighted average of 90% probability pixels. So what it means is basically looking at this sky map, we take 90% probability pixels and we weight average those by probability to get like the weighted average probability. And for this sky map, it would be this blue star. And the true location is this blue star. So you can see that both of these quantities measure different things, and you can imagine that in some cases you will want to use one, and in some other cases you will want to use another one. So this is about quantities, talking about blip glitches, starting from blip glitches. They're probably the simplest glitches, and these are like here, some examples on the right-hand side. These are just really like short duration excess power coming from noise. And for these blip glitches we tested, we used different trend parameters. So for BBH signals, we used half a second before and after the blip glitch. For NSBH, we used -1 second up to 9 seconds after that, and the same for BNS. And we used longer duration the blip glitch for NSBH and BNS signals just because the signals are longer. So we want to see how the tail of the signal is affected by blip glitch as well, not only the merger part. And then looking at the results. So for blips and BBH, you can see that basically localization difference is really like not changing much. At the whole time, it changes only at really like close to the blip glitch. So there are like 2 peaks. And looking more at that inner window, so looking at -100 milliseconds up to 100 milliseconds after the blip glitch happened, you can see that there are 2 peaks. There's one peak at 30 milliseconds, and there's another peak at about -90 milliseconds. So looking more closely at that 30 millisecond peak, what we found out that actually it is basically a destructive interference. So just looking at the plot at this upper right-hand side plot, you can see that there's like, well, this is how it looks like. Essentially, you have a blip glitch on the right-hand side, and there's that BBH signal. And if they are overlapping, so this is the plot at 30 milliseconds after that, you can see that there's some missing power in the middle. And we looked more closely at that. We looked at the time series data, and this is how it looks like. The orange represents real data, so this is like glitch and you could say Gaussian noise. And then blue is the gravitational wave signal. So you can see that basically that at this particular time, you can see that the phases are basically the opposite, but they are overlapping, and because basically they just cancel each other. So as I said, it's like destructive interference. So this happens at a very specific point at 30 milliseconds after the blip glitch. Talking about this other peak, we could not really find like a physical reason for that, because this happens before the actual blip glitch. And looking more closely at the data, it seems that this is actually skewed by one data point. So I mentioned previously that we are just taking like 10 blip glitches, for example, and we take the average of those 10 blip glitches. So there was just one sky map which was really like big at this particular time. So it is not really a physical effect. I would say this is just like some noise creeping over. So this is talking about BBHs, talking about NSBH localization distance. So just a reminder, we are going from -1 second up to 9 seconds. And firstly, what you can see here on the left-hand side plot is that you have much more noise coming here, comparing with the BBH signal. And this is reasonable because an SBH signal is much longer, so that the SNR per time frequency pixel, there's less SNR per time frequency pixel, and that means it basically gets more noise contribution as well. So you would expect to see more noise than for the BBH signal. But overall, you can see that basically there's something happening again, like next to the glitch. But apart from that, there just looks like there's just noise. That's it. And looking at this inner part of the glitch, so we did more injections at -25 milliseconds up to 100 milliseconds after the blip glitch happened. And you can see that there's something happening at around like 25 or maybe 30 milliseconds after the blip glitch happens. So we think that this is actually a very similar effect to that BBH that we talked about. So this is like that 30 millisecond effect. But again, like you can see that it is not really that prominent as with the BBH signal because of my previously explained the time frequency content of the signal. And then looking at the BNS, looking at the larger picture, you can see that there are like a couple of peaks, but apart from a couple of peaks, there's nothing really much happening. And then you can see, looking at that inner glitch duration plot, you can see that there are some peaks as well, but they are at different times. And you also can see that in some cases, the distance for Pmax probability is different than for distance for P90. So you can see that it's not really so clear cut. So we are not really sure what is happening here, but if I would need to interpret those results, I would say that this is just basically noise because, as I said, like the sky maps can get sometimes very noisy. And this is again just the effect of like noisy sky maps, because we would not see to have stronger effects for BNS signal compared with NSBH or BBH signal. So I would say that this is just coming from the noise itself, not from from Gaussian noise, not from glitches themselves. And then talking about other glitches, so thunderstorm glitches. So thunderstorm glitches are much more varied in morphology. So here you can see the right-hand side plots for a couple of examples of glitches. So frequency, strength, and duration can be very different for these glitches. So these are still the same class of glitches, but the morphologies can be quite different in the same class of glitches. So we use these run parameters on the left-hand side. So we use 2.5 seconds before and after the blip glitch, sorry, thunderstorm glitch. And then for NSBH and BNS signals, we use the same parameters, which is -2 seconds. Then we went for the whole duration of a glitch, and then +9 seconds. And then talking about fast scattering glitches, they also are very complicated in morphology, much more complicated than blip glitches. Here are a couple of examples. So you can see that they're like repeating themselves. They're quite similar, but at the same time, you can see that the frequency is different and like the frequency of repetition is different. So they are the same class, but they're quite different by themselves. And we use these run parameters, which is from -4 seconds to 28 seconds for BBH signals, and then the same parameters for NSBH and BNS signals as for the thunderstorm glitches. Now, talking about results for thunderstorms and scatterings, we saw no differences for BBH signals. And this is expected because BBH signals are very small time frequency content signals, so they're not really affected by this low time frequency glitches. But then for NSBH and BNS signals, the story is more complicated. So firstly, the problem is, as I said, is that glitches themselves are not very similar. So if we take like 10 thunderstorms and 10 scatterings, they're not really similar to each other. So because of that, the averaging results is not really that trivial as for blip glitches. So at the moment, what we see is that there are no conclusions, like no final or like no clear-cut results for NSBH and BNS sources for these type of glitches, for thunderstorms and scatterings. And we are not really sure why this is the case, and I will talk a bit later that in the summary. So talking about the summary, in summary, like generalizing thousands of sky maps is not really trivial. Localization distance from all these four quantities that I talked about, briefly presented, localization distance seems to be really the best quantity to see any differences. Now there is no really difference for two detector detections or like weak three detector detections, but because at that point the sky error is still quite huge, and when there's that really huge sky error, it just basically Gaussian noise is more important, or like it introduces more errors than blip glitches, thunderstorms, or scatterings at that time. But if you have more confident three detector detections with like SNR 40, which is possible in O4, for example, then you would have, then it can be impacted. So talking about the impact, BBH signals, so GW1509 type or 0914 type signals are affected only by blips and at a very specific time, so about 30 milliseconds after the blip glitch happened. And then we can see a similar effect for NSBH signals, but it appears that there's no similar effect for the BNS signal. And this is, as I said, like it can be explained just by time frequency content and SNR per time frequency pixel, essentially. Then for NSBH and BNS signals and thunderstorm and scattering glitches, this is more complicated. And currently the results are not conclusive. And there are two explanations for that. So is it because there are no conclusions? So glitches are just like affected, but there's like no really clear way of measure that. Or maybe the problem is that glitches are like so complicated in morphology between themselves. So like thunderstorms, they're like so different in themselves that there's really no reason to average those out. And basically by averaging out, we are just losing some information and we are losing just some useful differences. So this could also be the case. So I'm not really sure what is happening at the moment about this. So that's why I think so in future, we would like to look at one, like for example, thunderstorm glitch much more closely. So do much more injections with finer spacing with different SNRs and try to see if we can understand just one glitch, and maybe then we can draw some conclusions, because averaging seems that it's not really working at the moment. So yes, that is it, and I'm happy to take any questions if you have.
Thank you very much, Ronaldas. Questions, please. Go ahead, Mariella.
Hi, so I think my question, unless I'm understanding things wrong, so how accurate then can you say if there's a detection that we see, but there's a glitch that occur at the same time? With how much accuracy can we say, well, that's definitely a source that we're detecting and not a glitch? Or do we just ignore, because if they're too close together, then we just say, we're not sure, let's just not ignore this.
Yeah.
What's the accuracy?
So detection, like the accuracy of detection itself is quite high. Like, for example, PC Live is able to discriminate glitches and signals quite well. So for example, like when I did these injections, there was always a detection even if there's a glitch nearby. So detection always happens, and this is not a problem. The question is how accurate the sky map is. And like looking at these results, it seems that for BBH, for example, only the blip glitches matter, and they matter at a very specific time. So for example, if there would be a detection, and if there's a blip glitch nearby, most of the times, I would say almost never, we would care about that blip glitch unless it is at that very specific point, which is about that 30 millisecond after the blip glitch. But if there's a blip glitch, for example, like if there's a signal and there's a blip glitch happening like exactly on top of it at exactly the same millisecond, then because it is multi-IFO detection, so that signal happens at Hanford, at Livingston, and at Virgo, then this, the detection pipeline is still able to see that this is actually a detection and not a glitch, and it is still able to differentiate that. So yeah, I would say that detection pipelines are quite good at that.
More questions?
Thank you.
Go ahead, Alejandro.
Yes. Maybe you already said this. I've missed parts of the your presentation due to connectivity, but I was wondering, how does this scales with the signal to noise ratio? Like, is it important how strong the signal to noise ratio is, or is there just some like basic level which needs to be surpassed and then it doesn't matter?
Yeah, so it definitely matters. Like, for example, initially we did signals injections with SNR 20, and we actually saw no effect. So we basically just saw that there's random things happening. So at SNR 20 at Livingston, the network SNR was about like 30 in total. And basically at this SNR, it doesn't really matter that much. And the reason for that is because at Virgo, the SNR becomes, instead of 11, the SNR becomes about like 7, like 6 or 7, something in between. And at this SNR, it means essentially that it is like very close to Gaussian noise, because like Gaussian noise, well, it depends what you ask, but it usually is like considered like something above, like something about 6. So if the signal in the third detector is similar to Gaussian noise, then basically it becomes, the sky location gets really bad. So that's why you want to have a confident 3 detector detection. So that's why we chose this SNR of 30. So if you would choose like higher SNR, which is like, for example, SNR at Livingston 40, then the Virgo SNR would be even higher. So at that, we would see this effect more strongly. But basically, you need to have like strong 3 detector detection to see any differences. But if you do not have 3 detector confident detection, then basically Gaussian noise is going to have more differences than any of these glitches that we tested.
Okay, thank you.
Actually, on a similar note, I have a question, which is you showed that the blip glitches had some effect on the louder BBHs like 915 or 914. Have you tried to tune the strength of the glitches to see at what minimum levels that will have an effect?
Good question. And yes, we actually did not do that. So we looked at like vanilla blip glitches, I would say. So these are like glitches with SNR of like 20 to 30 or something like that. We didn't choose like very strong SNR, like 50 or 60. So like, I would say strong SNR blip glitches. Thinking about that, if it would be smaller SNR glitches, because like the majority of glitches are of course like smaller SNRs, so I would expect to have them less difference, because like looking at this, like this plot on the left hand side, you can see that in order to have this cancellation of powers, you need to have that the powers would be similar size, because like if, for example, there is that blip glitch which is like much smaller, then of course you wouldn't have that disruption and interference which is happening at the moment. Well, you would still have it, but there would be still some extra power left. So I think so this is a very good point that you bring up here, because yes, it also depends on the glitches SNR. The problem is that if you want to do like averaging, then you need, like, we would need to do much more runs. So to answer your question fully, I would say that it should matter. And I think so lower SNR blip glitches would have less effect for this particular thing.
Yeah, I don't doubt that lesser SNR will have a less effect, but my thinking was that smaller SNR glitches would be less straightforward to identify, let's say, and those were the ones that can cause hidden problems underneath, where you get a result and you have a systematic because of the glitch, but it's not obvious that the glitch is actually there because you can't just look at it. You kind of see what I mean.
Okay, so yeah, I think so I understand the question. Talking about the sky maps, like I do not know about other parameters, but talking about the sky maps, I would say that there would be no real that much of a difference, because doing all these runs, what I noticed just like random Gaussian noise introduces a lot of errors. Like in parameter estimation and like offline searches, this is a bit different case because they have like all these other tools. But in low latency, it seems that the Gaussian noise, just like going from 1 second to another second, you can sometimes get like very different sky map just because of Gaussian noise. So if we have this small SNR glitch, I would say that it could impact the sky location, and it probably is going to impact sky location, or like at least in some cases. But the thing is that the Gaussian noise itself impacts sky location as well. So if the errors from Gaussian noises are like larger, then you could say that it doesn't really matter that much.
Sure. Although I would argue, okay, that error from Gaussian noises would be within what you expect for the interpretation of the posterior, right? Because the posterior will move, because of the nature of statistics. The glitch would make it systematic, but then I guess if you didn't know that the glitch was there, then and if still within the statistical fluctuation, it doesn't matter. So I see your point as well. Yes.
Yeah, like we didn't really look at parameter estimation as per se. We looked only at the sky location, which is of course like only part of it, only part of the parameter estimation.
Thanks, Ronaldas. More questions for Ronaldas? Okay, if there are no more questions for Ronaldas, then let's thank Ronaldas, and thanks again, both speakers, Alejandro and Ronaldas. Yes, for both very interesting talks, actually.